Today we're going to go over the North Carolina Math 1 released items, questions 44 through 47. Okay, if this was an online question, you would probably just select by clicking each statement that can be modeled with a linear function. So keyword here, we're looking for the situations that can model a linear function. So remember, with a linear function, we need to have a starting amount and then a constant rate of change. So M would be that constant rate of change, and B would be that initial amount, also known as the y-intercept. Okay, the first statement says a taxi charges an initial fee of $2 and $1.50 for each additional mile. So yes, this would work because $2 is your initial fee, keyword initial, and then you're paying $1.50 per mile. So that would be your rate of change. Okay, the second one says the population is in a town decreases by 15%. Remember, when it decreases by 1%, this is exponential, so this is not linear. An airplane flying at an altitude of 33,000 feet descends at a rate of 20 feet per minute. So the altitude has a starting height of 33,000 feet, and it is descending at a rate of 20 feet per minute. So this would have a negative rate of change. A pizza restaurant charges $5.50 per pizza and 50 cents for each additional topping. So this is your initial fee, this is your rate of change. And a cell doubles in size every 2 hours. Remember, if something doubles, you're multiplying by 2, so that is also exponential. So we have 3 different situations that are linear. So the taxi, the airplane, and the cost for a pizza. Okay, 45 says, what is the distance between the y-intercept of the function f of x equals 2x squared minus 6x plus 3, and the y-intercept of the linear function g represented by the table below? Okay, the first function, this is a quadratic. I'm just going to highlight that. And I do notice that this quadratic equation is written in standard form. And when the equation is in standard form, your c value is your y-intercept. So this function has a y-intercept equal to 3. And then it tells us that the table is a linear function. So a couple things we could do. We could do it algebraically, but since I have Desmos, I'm going to take a picture of my data real quick, and I'm going to go over to my Desmos graphing calculator. And since we're looking for a linear function, we can do the linear regression. So we're going to click plus sign table. My values for x are -5, -2, 2, +5. My y values are 15, 3, -13, -25. Whoops, that needs to go down a line. -25. Okay, so if I click the magnifying glass real quick, you can see the line, the points lining up linearly. It looks like it's going to hit, I don't know, somewhere maybe -1, -2, maybe even -1.5. So we're going to say y1 is approximately mx1 plus b. And my y-intercept, I wasn't zoomed in. So if I zoom in, I can see exactly it's hitting at 5. I was on a different interval. So my y-intercept, if you look in the box where we've done our calculation, the y-intercept is -5. You can also click on the graph now and see the y-intercept of the line. Okay, so the y-intercept of the linear equals -5. Let me actually write y-intercept. Okay, go back to the question. The question says, what is the distance? So when we calculate distance, we're going to subtract. So we're going to take 3 and subtract -5. Remember, when you subtract a negative, that changes to plus a positive. So 3 plus 5 equals 8. You could also graph your y-intercepts. You have one y-intercept at +3. You have another y-intercept at -5. And you could count 1, 2, 3, 4, 5, 6, 7, 8. So that is a distance of 8 units. .46 says the table below displays the walking heart rate and running heart rate of 8 girls in beats per minute. Using the linear best fit model for the data, what is the predicted running? So we want the predicted, so that's going to be from the model. The predicted running heart rate of a girl whose walking heart rate is 100 beats per minute. Notice walking is in the first column, so that is your value for X.
Staff, may I have your attention? The baby shower is starting in the back-end corner at this time.
Okay, so if we look, the beats, the walking heart rate, this is going to be X equals 100. Okay, we're going to go to Desmos. Click plus table. We're going to add our values for X first, so 66, 72, 74, 78, 80, 84, 86, 88. Okay, 128, 136, whoops, I forgot to press enter, 136, 134, 138, 142, 146, 148, 152. Again, linear regression, so make sure you have this equation memorized for your exam. Y1 is approximately mx1 plus b. I'm going to click zoom to get a better window. There's a couple ways you can do this. You can actually trace the line, and we want to trace the line and find where x equals 100. Let me have it over some. It's easier to do this on your mouse probably than me using the iPad, but there it is. 100 gives us a prediction of 162.8. So 162.8. You will notice the numbers are rounded to the nearest whole. So this 8 will round our 2 up. So that's 163 beats per minute. Okay, this next one says, please click and drag. So this would be a drag and drop on the computer test. It says we're looking for data that is symmetric about the mean. We're looking for data that is skewed left, data that is skewed right. So if we look at the numbers, you could put this into your calculator, but it's actually pretty easy to determine based on the data we're given. So we have 15, 25, 35, 45, 55. So each of those numbers are increasing by 10. We have this pattern, plus 10, plus 10, plus 10, until we get from 55 to 115, and notice it is increasing 60. So this number definitely stands out to me as an oddball. And it's a number that is on the upper end of the data. So higher numbers are going to be to the right. So this higher number will skew the data to the right. So this is going to go skewed right. Okay, if you look at your next set of data, we're going 15 to 75, so that's plus 60. Then we start increasing by 10, 10, 10, and so forth. This time we have a number that has a much bigger difference or much bigger amount of change on the left side. So it's on the lower end. So that 15 is going to skew our data to the left. So if you have a low outlier, it skews the data left. If you have a high outlier, it skews the data right. And if you look at the next data set, it's increasing 10, 10, 10, and so forth. So this is symmetric data. If you graph this and look at a bar graph, you can look at the side that has the longest tail. You can also look at a box and whisker plot to see which side the longest whisker is on. But for this set of data, I think it's pretty simple to see which one is skewed right, left, or symmetric.